Hi everyone, welcome to my channel. In this video, we are going to discuss the concept of motional EMF. Now, motional EMF implies the EMF induced across the two ends of a conductor which is moving in a magnetic field. Now, suppose you have a U-shaped wire. Okay. Now, this is a conducting wire of negligible resistance. Okay. And so this wire is placed in a horizontal plane. So it is placed in a horizontal plane, in this plane. Okay. And you have a rod. This rod is of length L. Now, see this U-shaped wire, it is placed in the horizontal plane, and the rod, it is placed like this on the U-shaped wire. Okay. And this rod, it is conducting, but it has finite resistance. This U-shaped wire, it is conducting, but its resistance is negligible. Okay. Now this rod, so you have this U-shaped wire placed like this, the rod is placed like this rod is of length L. Now this rod can slide over this U-shaped wire. Okay. And we are assuming that there is no friction between the rod and this U-shaped wire. Okay. And suppose you have a transverse magnetic field in this region. So magnetic field is perpendicular to this plane and it is directed inward. Okay. So if the plane is horizontal, then magnetic field will be directed in the downward direction. Now suppose this rod, it is pulled in this direction with velocity v. Okay. With the constant velocity v, you are pulling this rod in this direction with velocity v. Okay. Now suppose this is the position of the rod at time t equal to 0. Okay. And this rod moves to this position at time t is equal to dt. So it has moved from this position to this position in time dt by traveling a distance dx. Okay. So now see, when the rod was at this particular position, so the flux will be due to this entire area, isn't it? This entire area, flux will be through this area. Now when the rod moves to this position, now the flux will be due to this area. So there is a change in area. Okay. Now flux, see, flux is BA cos theta. Okay. Flux is BA cos theta, where theta is the angle between B and A, isn't it? So in this case, magnetic field, it is perpendicular to the plane and area vector is also in the inward direction. So this theta is equal to 0. Okay. So we have cos 0, phi equal to BA cos 0, that is equal to phi equal to BA. Okay. B is constant, B is not changing here. What is changing here? Area. Area is decreasing. So what is the decrease in area? This is the decrease in area, isn't it? Now since there is a decrease in area, so there is a change in the flux, and if there is a change in the flux, there will be induced EMF. That is the concept of electromagnetic induction and Faraday law, isn't it? So EMF induced, from Faraday law we have EMF induced equal to d phi by dt. Okay. So now EMF is equal to B dA by dt. Okay. So this d phi is replaced by B dA using this. Okay. Achha. Now what is dA? dA is the change in area, that is this part. Okay. So what will be the area of this part? Length of the rod is L and this is dx. So this area will be L into dx. So this quantity dA, this can be replaced by L dx. So this is EMF is equal to B L dx by dt. So this rod is moving through a distance dx in time dt, and what is the velocity? Velocity is v. This rod is pulled by you by an external force with velocity v. It is moving with the constant velocity v. So this dx by dt, it can be replaced by v, velocity of the rod. So we have E is equal to BL V. So this is the expression for motional EMF. Okay, this is the expression for motional EMF. And why it is called motional EMF? Because this is the EMF induced across the two ends of the rod, which is moving in a magnetic field. Okay, so this is one approach. Okay, there is another approach to this concept. When this conductor of length L, this rod of length L, it is pulled in this direction with the velocity v, the free electrons in this will experience a force due to the magnetic field. Why? Because of magnetic Lorentz force. Magnetic Lorentz force, magnetic Lorentz force. This is the force experienced by a charged particle moving in a magnetic field. Okay, so this Lorentz force F is equal to Q VB. Okay, it is Q V cross B, but here velocity is in this plane and magnetic field is perpendicular to the plane. So angle between them is 90 degree. So it is VB sin 90. So I have written VB, Q VB. Q is the electron charge. Okay, now what is the direction of this force? Okay, so we have to use right hand rule. Electron is negatively charged particle, so we have to use right hand rule. So this conductor is moving in this direction, magnetic field is in the inward direction, so force on the electron will be in the upward direction, so the electrons will move in the upward direction. So this electrons will move through a length L, isn't it, under the action of this force F. So what will be the work done? Work done is force times distance traveled, displacement is L. So work done is equal to force is this, so QVB times L, isn't it? Now what is the EMF? EMF is work done per unit charge. EMF is work done per unit charge. Work done is this quantity, so this is QVB L divided by Q. So this Q cancels out and we have EMF is equal to BLV. So this is another approach to the same concept and same expression of motional EMF. This is using concept of magnetic Lorentz force. Okay. Now interestingly, there is also a third approach to this. Okay. Now third approach is, see, this magnetic Lorentz force, it is causing the electrons to move in the upward direction. So there is an accumulation of negative charge at the upper end. Okay. So if the electron, there is excess of electron in this side. So for every electron moving to this side, there will be a positive charge on this side. Okay. Now initially only few electrons will be there. So small negative charge, small positive charge. But as the process goes on, there is a large buildup of negative charge over here and positive charge over here. So there will be attractive force due to electric field, isn't it? Because negative charge and positive charge, they will experience attractive force. Opposite charges attracts. Now that is force due to electric field. Okay, but what is causing this separation of charges? Positive charge this side, negative charge this side. Who is causing this? The magnetic Lorentz force. So magnetic Lorentz force is causing accumulation of negative charge at this point, accumulation of positive charge at this point, and this electrostatic force is causing the opposite of that. It is causing them to bring them together. So at equilibrium, what will happen? This electrostatic force will balance the magnetic Lorentz force. See, magnetic Lorentz force is causing the electron to go in that direction. Electric force is pulling it back, isn't it? So F is equal to FB. This is the force due to electrostatic force. This is the force due to magnetic force. So what is the force due to electrostatic force on the charge on the electron? Q into E. F is equal to QE. And this is QVB. This is electric field. This is magnetic field. So this QQ cancels out. So we have E is equal to V into B. Okay. So now this E is the electric field. It is EMF per unit length. Electric field is potential gradient, negative of potential gradient. E is equal to minus dV by dr, that we have seen previously in the chapter electrostatics. So this is E is equal to EMF divided by L. EMF is the potential difference developed. So this is E by L equal to V into B. So E is equal to BL V. So this is another approach to the same concept. Now here one thing is to be seen. See, in this case, V and B, V is in the plane and B is perpendicular to the plane. So V and B are mutually perpendicular, but in some cases they may not be perpendicular. Okay, so in that case, this expression will be V cross B. Okay, this is electric field. So we have electric field is equal to V cross B. Okay, now this is E is equal to E by L. Okay, now L is a vector quantity, this is a vector quantity. Now when you equate these two, this vector quantity will be multiplied by this vector quantity to get a scalar quantity. So what kind of multiplication will that be? Will it be a cross product or dot product? Dot product. So this is EMF is equal to L dot V cross B. So this is the expression for EMF. Okay, when these quantities are in vector form. Okay, now you can use this expression to find the direction in which in a conductor you have high potential. That is V cross B, the direction of V cross B. The direction of V cross B will always give you the end of the conductor at which you have high potential. Like in this case, V is in this direction, V is in this direction, isn't it? V is in this direction, magnetic field is in the inward direction. So V cross B, it will be in the downward direction. So V cross B will always point in the direction of high potential. Okay, V cross B will always point in the direction of high potential. See, in this case, electrons are moving in the upward direction. So here you have negative potential, here you have positive potential. So this side you have high potential, isn't it? Okay, so this is the expression for motional EMF, and these are the three approaches to the concept of motional EMF.